Hello, in this lesson, we're going to continue to talk about solving absolute value inequalities. I'd like to clarify something here. I think the picture I put here to summarize the less than equals to case may be confusing. So I'm going to change this right here to be just one dot. Okay, because looking at the situation we had, with other cases, right? So I just want to go ahead to put this dot here, so it's not being confused by it. Okay, so let me make that correction to see. So this is going to be one dot, one red dot. Okay, so this way it would be consistent, right? Because I don't want to be confused to think that all of these numbers are solution. In fact, in this case, there's only one solution, which is 0, right? And in these cases, it's this interval between -2 to +2. And in this case, it's between -2 to +2, which is an open interval. Okay, so I'm going to also put AKA, right? This is something you guys saw in the last lecture, which is, I'm going to also put the interval, okay, interval right here. And this one, I will put an AKA, even though I put AKA, but also known as, I still prefer you guys use the inequality, okay? The inequality form is most useful, In this case, there's not an interval because it's just one point and no solution, right? So this is the summary we had for, solving absolute value inequalities in the cases that less than or less than equal to, less than or less than equal to. Okay, and today we're going to talk about how we solve inequalities which are greater than or greater than equal to. Okay, do we have these cases? Yes, we do. Okay, and so I'm going to bring this under to the top. Okay, I'm going to bring this to the top. Okay, and when solve these inequalities, in the case of greater than or greater than equal to, we also have these cases. Okay, so I want you to see this comparative study and how it's been done, right? And then we're going to go ahead and talk about the meaning. We're going to talk about the meaning. So with that understood, and of course, the cases we're going to study, is going to be, well, all of these pictures will have to be redrawn. Okay, all of these pictures will have to be redone because we're going to change to be greater than, right? And this is going to be greater than or equal to, and this is going to be greater than or equal to 0. Okay, and this is going to be greater than 0. And this is going to be greater than -2. And the next one probably would be greater than or equals to -2. So we have all of these cases. And the conclusion we're going to draw is going to be completely different. So all of these pictures will have to be redone. Okay, so all of these pictures will have to be redone. Okay, so without further ado, we're going to remove the rest of the table. Okay, so all of these answers will no longer be relevant. They will not be relevant. And we're just going to discuss these cases. So we can call this a case study. Once again, the lesson we have here is not to provide you with tables so you will memorize. Okay, trust me, if you don't understand by simply memorizing it, it's not going to help you. It's not going to help because you'll get confused. There's too much to remember. Okay, so the only way to really master this material is just to understand it. Okay, so understand it. So we're gonna discuss the greater than, equal to. All right, so the first case. Okay, so we're gonna have an example to discuss, and of course we're gonna study the simple case. Instead of using omega, we're gonna consider x in this simple case. Okay. All right, so the situation is very similar. It's very similar. So we consider the simplest case possible, right? And we're going to use definition. We're going to use the function perspective, and we're going to use function to explain and illustrate how to solve these inequalities, okay? And I also wish to bring the picture to our study, right? We had a picture, didn't we? We had these pictures that we have used, we created and used, right? So the one is a function perspective, and the other one is the definition of absolute value. So we bring these two at our disposal. Okay, so example number one. Okay, solve for x. Okay, so the inequality we have, right, we already set up, we're going to do this one. Okay, now what does it mean? Right, input x, the function, okay, the function which is absolute value, of x, right? And we know the output, we want the output to be, absolute value of x is the output. We want the output to be greater than 2. So that's the function perspective. And we want to identify, okay, so what is wanted, right? We want to identify all inputs such that their outputs is greater than 2. Okay, and we know input is a horizontal measurement and output is vertical measurement. So let's look at the first method. Method 1, right? Understanding the picture, right? You're pretty familiar with this procedure, right? We have this function, right? This is the graph of the function. And let me just make a little adjustment here, right? So this is the function. We want the output to be larger than 2. What is 2, right? Larger than 2 does not include equals to 2. So we're going to draw a horizontal line. That horizontal line, I'm going to draw it red, okay? Broken line. Why broken line? Because equals to 2 will be solid line. It's a broken line, so that's the line we're going to draw. So this line is the criteria for, because beneath it, right, any output that's lower, that's less than 2. Any output that's higher, that's larger than 2. And will these 2 dots included? No, these 2 dots will not be included because they will cause the absolute value equals to 2, right? Equals to are not included. And therefore, we know what we want. We want the output to be larger than 2, not smaller than 2, right? So this is the case. That the absolute value is larger than 2. And this is the case, this shorter red line is the case that the absolute value is less than 2. Right? So these 2 dots here, we're going to turn them into circles. Okay, so let me find those dots. Let's see. Okay, we're going to turn them into circles. Okay. Circles. There you go. Yep. Okay, so we can see all the input such that the output is higher than 2. The output is higher than 2. And where do we find those inputs? And those inputs can be found here. Those are the input. Those is where we find the inputs such that their outputs is larger than 2. We can also find those inputs over here. Okay, anything in between -2, +2, or equals to -2, or equals to +2, those inputs will not be the input such that the output is larger than 2. Okay, so with that understanding, I'm going to redraw the picture, and so that you can understand what I'm talking about. Okay, so we have identified these inputs, right? So what are these inputs? These inputs are going to be like this. Okay, -2, 0, right? And we're going to draw these lines. And these are red, thick. Okay, so those, but not including -2. So at here, we're going to have -2, 0. That point is not included. Whoops, how did I have a dot there? Sorry, I need to redo that. It should be a circle. Okay, it should be a circle, not a dot. Okay, so this tells us that all of these points, okay, all of those points, their output are going to be higher than 2, right? So we know the level of 2. So all of these outputs are higher than 2. So they satisfy the condition. They satisfy the if, okay? They satisfy this if. So all of these are solutions. But we want to find all of them, right? So we have more. And what is more? Where are they? They are here. Okay, they are here, right there. Okay, 2, 0, and we should have a dot, but we should have a circle, not a dot. So all of these number 2. Right, so you can see all of these outputs, right? All of these outputs, input, output, right? Input, output, right? Input, output. All of these outputs, you can see those are the outputs. Those outputs are higher than 2, higher than 2. So needless to say, the solution are all the numbers less than -2, or all the numbers larger than 2. So how do we express that? How do we express that? Well, this is how we express it. Okay, this is how we express it. I'm going to express it underneath. I'm going to express it underneath this piece. Okay, all of these numbers, right? Suppose I pick a representative here. Okay, and I'm going to put an X over there. Okay, I'm going to put an X over there. X. Okay, so that's going to be say this is 0.0. 1. And I'm going to mark this. I'm going to show you how to show it, how to come up with the right inequality. So these are axes, right? Those are the solutions we want. And there's another one. Okay, so those are axes too. And over here, right there. Okay, so how do we express all of these numbers to the left of -2? Well, every number to the left of -2, they are smaller than -2. So we will write it as x less than -2. Okay, on the other side, how do we express it? The other side, I see all the numbers to the right of 2, and those numbers can be expressed as x is larger than 2. And how do we connect these two? Why or? Okay, because if you pick any number from less than -2, and that output will be greater than 2, okay? And we don't need any other attachment, right? The if statement is satisfied. If we pick any number which is larger than 2 on this side, it will also cause the output to be larger than 2. Therefore, the solution is x less than -2 or x is greater than 2. So this is the one case we have studied. Okay, so what we'd like to do is that we're going to put this case in our summary, right? We're going to put these cases in our summary. Why not? Right. So as we're doing it, we get those pictures, right? And we're going to put those pictures in our summary table. Okay. And what is more, we're gonna have 2 rows, right? And the solution, of course, is x is less than -2 or x is larger than 2. The or case. Okay, the or case. The or case. And of course, we're going to do the solution. We're going to do the solution using definition. We're going to do the solution using definition. So that's the first method. How do you show work? I mean, show work to solve this inequality, right? So you copy the question, then you show your work, and that's all you need to do. If you choose to use the function method. Okay, and the picture will help tremendously. Okay, so let's look at method 2. Method 2, we're going to use definition. Right? For definition, then we don't treat it as a function. We just use definition. And the situation we have here is solving for x. Right? Solving for x right here. Okay, solving for x. We know that absolute value of x. Okay, absolute value of x is the distance, right? Is the distance between x and 0 and the origin. Okay, between x and 0. Okay, if this is the situation, right? We don't know what x is, but we know where 0 is. So we just measure the distance to be larger than 2. We measure the distance to be larger than 2. How do we measure? We can measure from 0, right? If we measure from 0, that distance is 1, more than 1, 2, but we want to be more than 2, and there you go. We found a number. On the other side, and this distance is less than 2, less than 2, equals to 2, more than 2, right? So we realize then our solution actually are going to be over here, not including -2 or +2. Okay, because at those points the solutions are, you know, they're more than, so this is how we located the solution. And let's mark these solutions. Okay, so let's mark these solutions. Okay, I hope you understand what I'm doing here. Okay, so the solution will be, once again, right, -2, 0, and this point is going to be a circle, not included. Okay, and another point is 2, 0. It's going to be a circle, and also lots of inputs. Okay, and that's going to be a line. We make it thick. And another one right there. So it's really the same idea, isn't it? Okay, one is the 2-dimensional, the one we just did, method 1 is 2-dimensional, and the other one is 1-dimensional. And in terms of showing work, right, in terms of showing work, and all you have to show is that you give the solution as x less than -2, or x is larger than 2. Okay, we have not addressed very much about the interval representation. Okay, I'm sure some of you are familiar with the interval representation. The interval representation, okay, I'm going to put it as a note. The interval representation, if I teach it, right, they are less useful as the inequality representation. Okay, so the interval representation will typically be like this. Okay, that's the interval solution. Solution express, okay, in interval. Okay. In my teaching experience, I found these intervals, even though they're very useful, and they're not as useful as these inequality. So for teaching this course, I will emphasize the use of inequality. I will emphasize the use of inequality, okay? So let's put this in our summary. Right there, right? You can see they're so similar, right? There's a lot of similarity. There's a lot of similarity. But if you compare, if you would compare with what we did with less than case, right? So if you put these two tables side by side, and you will really have seen a lot more insight, right? You will see a lot of insight. But anyway, so this is the case, which is a common case, right? The next example, of course, is greater than or equals to 2, right? Greater than or equals to 2. And this time, okay, let's see example number 2. Okay, still solve for x, that if statement, right? And the inequality is greater than or equals to 2. We have done greater than 2, we have done equal to 2, right? Which we done equal to 2. So only difference between these two methods, right? For greater than is going to be including it will be including the point at the endpoints, right? So the first method, everything being similar, right? Greater than or equals to 2. And now all these circles, the red circles are going to be dots. So this is less than or equal, greater than or equal, and the picture will be drawn over. Okay, so this time it's going to be a dot, right? One more dot. And we have 2 more dots. more dot. One more dot. There you go. Okay, the only difference is that equal to 2, the output, when the output is equal to 2 will also be solution. So as a result, our solution will be x less than equals to -2 or greater than or equals to 2. On the second method, right, on the second method, right, for the same question, if we use definition, right, everything will be the same, but the circle will be turned into dots. The circle will turn into dots. Okay, let's turn the circle to dot. Turn the circle to dot. There we go, right there. So that's a solution. That's a solution. Okay, and in terms of showing work, it's really just 1 or 2 lines, just one, 2 lines, right? That's a solution. I have a note for the interval. Once again, the interval notation is not as useful. Okay, it's not as useful, but it's worth mentioning. A lot of you probably is rather good at using these intervals. Okay, so this is solution union, right? Something like this, 2 comma infinity. 2 comma infinity. With that said and done, we want to see, we want to put these as our, to compare, right? For our comparison. So greater than equals to 2, right? So I'm going to put these in place and put it in our table, right? Greater than equals to 2. And the solution that is like that, right? Over here. And the solution almost the same, but less than turn into less than or equal to, greater than turn into greater than or equal to. Okay. So that's the second case. I'm actually going to bring this table with us, okay, because yeah, I think this will be fine. Okay, we're going to bring this table with us for our convenience of comparison. Okay, so we did first case, second case. Let's look at this third case. The third case, example number 3. Okay, example number 3. Example number 3, we have an inequality. Solve for x. Solve for x. Okay, where the absolute value of x is at least 0, greater than or equal to 0. Greater than or equal to 0. What does that mean? Once again, input for the function absolute value of x. Okay, produces output, and we want the output to be greater than or equal to 0. Right? If we look at the picture, right? If we look at the function perspective, right? Method 1. If we look at the picture, for input 0, the output is 0. Okay, so output. So for output equal to 0, the input will be 0. For input of not equal to 0, the output will surely be larger than 0. Right? So every single input will make the absolute value greater than or equal to 0 true. Because look, all of these outputs, all of these outputs. So the solution is what? The solution is what? Every input will guarantee, okay, every input will guarantee its output is at least 0. So the solution really is what? All real numbers, all real numbers. All of these numbers are solutions, okay? All of these real numbers are solutions, okay? So in this case, the solution is all real numbers. So I'm going to draw that horizontal line, okay? I'm going to draw that. This means every single inputs in the domain of absolute value of x and their output, okay, which are these vertical line we just drew. Every input, output, that input is greater than 0. That output is greater than 0. That input is 0, output is 0. That input is 0.7, output is greater than 0. Does that make sense? Okay, so for that reason, the solution, what do you think will be the solution? The solution is all real numbers. Every real number is a solution. Compare with less than or equal to 0. Compare, okay, compare with absolute value less than or equal to 0. What's the difference? What's the difference, right? So one is greater than or equal to 0. The other one is less than or equal to 0. So in this case, the solution is all real numbers. All real numbers. Okay, the solution is all real numbers. Wait. Okay, the solution is all real numbers. So I can use interval from -infinity to +infinity for all real numbers. You can also write the word all real numbers. All real numbers. Okay. Using definition. I would say in this case, we can use the range of absolute value function to make our case. We can use the range of our absolute value function to make our case. Okay. So method 2, we're going to say because the absolute value of x is greater than or equal to 0, right? For any real number, x, for any real number x, therefore, thus, the solution is all real numbers. All real numbers, right? So if we are to draw that picture, and that picture would be similar, So I would be drawing this picture, and on this picture, okay, in this picture, and we're gonna show that it's all real numbers. I'm just for drawing this picture. Okay, so it's red, indicating that every real number is a solution. Every real number is a solution. So I'm going to put this case for that. Okay. Oops. Right there. Okay, so we have studied 1, 2, 3. We have studied 3 cases. 3 cases. Okay, we have studied 3 cases. So how about larger than 0? How about larger than 0? How about larger than 0? Okay, so that's our next example. Example number 4. Example number 4. Example number 4. Example number 4. Okay, so when we're solving for x, we solve for x, the absolute value is larger than 0. How do we solve that? And once again, we use the first method from the function perspective, right? First method, not second, the first method from the function perspective, right? We solve this inequality and we're looking for all possible solutions, right? We know that input x given to the function, it produces output and the output has to be positive. The output cannot be 0, cannot be negative. So if the output is positive, so in what case the output is positive? Right? In what case the output is positive? So we're gonna be positive, right? And remember, we want the output to be positive, which is to be larger than 0, to be larger than 0, right? So you can also draw this horizontal line. You can also draw this horizontal line, right? Which is right here, right? Except you can see that every output for any input, right? So I'm going to draw a picture. I'm going to draw a picture. There's an input here. The output is larger than 0. That will be solution. This input will be solution. For this input, right? The output is larger than 0. So that input is a solution. And so we can keep going, right? All of these inputs whose output is positive, except 0, except 0. So in this picture, every input but 0 will guarantee the output is going to be positive. Therefore, we just have to turn this 0, 0 into a circle. Okay, so we're going to turn that dot into a circle. Meaning what? The rest of the input will be solution. The rest of the input will be solution, okay? So I'm going to graph the solution. The solution is going to be like this. Okay, so it's red, big, right? The next one, right there. And oh, I meant to have a red circle. One, give me a circle. Oh, red circle, sorry. I forgot to change the color. So the red circle, I hope you guys can see, okay? Every number is a solution but 0, okay? Every number is a solution but 0. How do we express that mathematically? How do we express that? So we have decided that solution, all real numbers, but 0. How do we express that? If the solution is all real numbers but 0, and this is how we express it. We express it as x is not equals to 0. So this means what? This means all real numbers but 0 is solution. So this is the expression by exclusion, So in this case, I'm kind of disappointed that this little circle is not that clear. Okay, it's not that clear. Let me see if I can make it a little clearer. Make a circle. Do you think that diamond may be better? No, it doesn't make much of difference. I really want to show that circle well to you. So let me try one more time. Okay, so I'm going to do this. To see if that helps. Huh, no. How about this? Nope. One more time, because I want to show that circle really well. I want to show that circle really well. Okay, see, that makes a difference. Not really, but you need to understand there's a circle there. Okay. Anyway, so the solution is just all real numbers but 0. Okay, so we're going to put that in the table. In this case, don't forget its meaning. We want the output. We want to find all the input such that their output is positive. So the solution is x is not 0. All real numbers but 0. Okay. On the number line, if we use definition to express it, right? Method 2. Okay. Using method 2, the expression will be very similar. Okay. It's also not including 0. It's also not including 0. Okay. Let me see if I can make this picture better. Okay, so we first draw that. Okay, 0, 0, red dot circle. So that's not included. And then all real numbers but 0, right? So okay, to see if that helps. And red, well, here, 0. And next one. To see if that will work better. Okay, this worked better. Maybe I can make the other one works better too. Why this is such a mess? There. Over there. Oh, I know why. I think I figured out. I made a mistake. This is better, right? Isn't this better? Yep, I think this circle shows better. So this one will be the, this one will also be better. Now we're going to put in the table for our comparison, right? So when we compare, hopefully this will help understanding. This will help understanding. Let's look at the next 2 cases. Let's look at the next 2 cases, right? Greater than -2, greater than or equal to -2. Greater than -2, what does that mean? We want output to be greater than or equals to -2. Okay, so this is going to be example number 4. And now it's example number 5. Okay. So what do we have here? We're solving for x, of course, once again, solve for x. Solve for x. Okay. So in this case, right, we have from the function perspective, right, we have absolute value of x, And we want the output to be larger than -2. Okay. The graph, if you look at the graph, right, I'm going to bring both graphs now. If you look at the graph, isn't this every output to be, isn't that every output is larger than -2? Because we want the output to be larger than -2, not smaller than -2, okay? You may think of, this is the place people tend to get confused, okay? Because we want the output to be less than -2 versus greater than -2. That makes a big difference, right? And you may say, oh, I'm going to draw a horizontal line. Sure, draw a horizontal line. Okay, you can even draw a broken line, right? Which is red. It doesn't touch. Doesn't touch doesn't mean there's no solution, because you have to look at the statement. The statement says we want all the solutions such that the output is larger than -2, right? So let's look at it one at a time. Okay, so I'm going to bring this down. I don't need this picture right now. Right? If you look at the input, right? If you look at, you just choose arbitrarily any input, right? Input here, and that's output. This output is positive. Is this positive number larger than -2? Yes. And if I choose input equals 0, the output is 0. Isn't 0 larger than -2? Yes. Then this number is what? Input, and that's the output. Isn't this output larger than -2? Yes. In other words, every output is larger than -2. So what do you think will be the solution? The solution is all real numbers. The solution is all real numbers. Okay, you actually don't really need, okay, you don't really need the horizontal line you drew there. We can simply use the range, the statement about domain and range of absolute value. Therefore, the solution in this case is all real numbers. And so I'm going to remove that broken line because it's really not useful here. Okay, not all lines you draw is useful. So what does this mean? It means every input is a solution. Okay, every input is a solution because every input is larger than -2. So that's the graph. That's the function perspective. Okay. On the other hand, since we talk about function perspective, right? So if this is what we wanted, the solution is what? Solution is all real numbers. All real numbers. Okay, the solution is all real numbers. In other words, from -infinity to +infinity, meaning that every input whose output is going to be larger than -2. And then you say, hey, wait a minute. We talk about the absolute value of any real number, which is positive or 0, right? Positive or 0. This is true for any real number x, right? If this is true, then 0 certainly is larger than -2, right? So this is forever true. So in other words, this statement, if we remove that, is true for any input, it's true. Therefore, the solution is all real numbers. So you can see that from the domain range perspective, as well. Okay. So how do you show work here? How do you show work here? you know, it's the key is that you must understand this concept, this narrative, the meaning of symbols, right? In terms of showing work, this is how much you need to show. Okay, so for X, then you can just simply say that if you want to, you can tell the reader solution, right? You can tell the reader this is the solution. And because if you like to really give a reason for the reader, which I usually appreciate, right? 0 is larger than -2 always. So every number whose absolute value is going to be larger than -2. So every number is going to be a solution. Okay, so this is this method. Okay, on the case that larger than -2. For that matter, larger than -3, larger than -10 will be the same thing, right? All real numbers. And this one is all real numbers but 0, right? So let's look at the second by definition, since you understand, right? So method 2, this is method 2. Okay, for method 2, of course, the distance between, X and 0 is always at least 0. And that, of course, is larger than 2. So when you use this picture, when you use number line to express our solution, what you can do, right? What you can do is just, why don't you let me? You know what? I'm just going to borrow this line, just remove the dot, remove the circle, right? So that's all. Sometimes the software is a little, has a temperament. And in this case, of course, we're going to remove that 0, right? And it's just going to be that. And that's it. The whole real number line. Okay, the entire number line for that case. Okay, and the solution is all real numbers from -infinity to +infinity. And last but not least, can you guess what will be the answer? All real numbers, right? All real numbers. Larger than -2, all real numbers. For larger, because this means X is larger than or equals to -2. For larger than -2, we have all real numbers. Equals to -2 will never happen. Therefore, the solution for this case is the same as the case right next to it. Oops, my bad. Okay, good. So everything is the same in this case. Okay, so if I make it a little smaller, maybe you can see all the cases. Okay, maybe the negative sign is not very clear. Is that better? Let me make them a little narrower so you see all the cases for your comparison. You can see all the cases for your comparison. In this situation, you really have to think on your thinking cap. Solving these inequalities involve absolute value. You must constantly think of the meaning. If you simply by memorizing certain format or relying on your memory, sooner or later you're going to make mistakes, get confused. Okay, and you can see this case And these two cases are the same thing. So maybe we can separate these two, right? We can separate these two. We can just switch these two, okay? So that's what I'm going to do. I'm going to insert a column, right? So let's move this piece over here, right? And move this piece over here. And that piece will be joining those other cases. And this piece we're going to remove. This column we're going to remove. What's so good about it? Why do I do this? This case is fairly common. This case is fairly common. This case is fairly common. And a little bit interesting. And the rest of the cases, the solution are all real numbers. Please be sure you understand the idea. You understand the meaning. Otherwise, with two tables, right? The table we did last time and the table we did this time, it's going to confuse you if you don't understand the meaning. Okay, so be sure you understand the meaning. Okay, so let's see how we're going to apply these scenarios. Okay, how we're going to apply these scenarios. Well, you can see as always, right? As always, I'm going to tweak this table, right? How am I going to tweak this table? I'm going to tweak this table so that, you know, X is no longer X anymore, right? We have a little more complex symbolically, this X actually is omega, right? So there's omega here. Omega. Omega simply means that as a placeholder, omega could represent, you know, anything. It could be a very complicated expression, right? And so all of these figures will be about omega. Okay, symbolic meaning. So that's the role of X, really. X is just a placeholder. Okay, think about that. X is just a placeholder. Okay, so when we get into more complicated situation, okay, let's see how many examples did we do? Example number 5. So let's look at some other examples. Okay, example number 6. Okay, I'm just making up stories. For example, I'm asking you to solve for X. I'm asking to solve for X. And here it's absolute value of X and not just X, right? So imagine this X becomes a complicated situation, right? So 2X minus 5, 3, how about 3X minus 5? Larger than 2, right? I'm going to make the fonts larger. So instead of one quantity larger, absolute value of one quantity larger than 2, now I have this piece, right? Understanding the scenario, we understand, right? This is the scenario that applied to our situation. So you have that in your mind. You have that in your mind. You don't have to show it. You don't have to show your teacher. And we know that if absolute value omega is larger than 2, then omega is either less than 2, negative 2, or bigger than 2. So we're going to take this piece, right? And we understand the picture and everything. So we start our solving process. Okay, you can see omega is 3x minus 5, or omega is larger than positive 2. Okay. And then we have two inequalities and we're going to solve it. We're going to solve it. And so we solve it one by one. Okay. In this case, they must be separated. They must be separated. Okay. I'm going to explain to you on the note. Okay. I'm going to explain this to on the note. Now, I'm going to add 5 on both sides. So I have 3x. Okay, I'm going to turn on the light. Okay. Adding 5 on both sides. And so we're going to get 5 minus 2. 5 minus 2 is 3. So on the inequality on the left-hand side, we get x is less than 1. Okay, x is less than 1. On the other side, we're going to add both sides by 5 again. Okay, 3x larger than 7. And I'm going to keep the or. Ideally, you keep it this way. You keep it this way, okay? X is larger than, divide both sides by 3, we get 7 over 3. And that's it. So that's our solution. So you tell the reader the solution is x less than 1 or larger than 7/3. Okay, and that's how you show your work. That's how you show work. Okay, that's how you show work. Okay. In this case, okay, I said I'm going to put a note here to talk about some common mistake. Some common mistake. Common mistake. I'm going to leave this. I'm going to leave this as a think out aloud. Out aloud, right here. And over here, the common mistake. Some of the common mistake I saw for these kind of situations, right? And we, typical, right? Mistake number 1. The first one, right? When people saw absolute value of x is larger than 2, some people will write it this way. They will write, they thought, oh, it's x less than -2, right? Less than -2. Or x is larger than 2. That's correct. But some people will invent the following. Okay, this is the correct, but they figure, oh, this I can put I can put it this way, right? X is less than -2 and x is larger than 2. So I'm going to put it like this way, 2. So they put it this way. This is all-time terrible, horrible mistake. Terrible, horrible mistakes. Okay, why? Why? First of all, whenever we write it in chain, like chain, right? It has to be an and relationship. It has to be an and relationship. And in our case, it's an or. Okay. This case, the solution is or. X is less than -2 or x is larger than 2. They cannot put on chain. Whenever you put on chain like this, it has to be an and relationship, but we have an or. You guys have studied, we studied truth table. We know about and or, right? We know about and or. Big difference between and or. And the second, right? On the other hand, is there such a number, right? So when you write it down like this, then you should ask yourself, is there a number? I'm writing it down, okay? Is there a number X? Okay, write it down the meaning, okay? Is there a number X such that X is smaller than -2 and larger than +2? Does such a number exist? Because when you write it this way, you're telling the reader this number X is larger than 2 and less than -2. Does such number exist? Okay, because this means, okay, this sentence means, okay, I'm going to write it down very carefully for you, because this is a very common, terrible, horrible mistake. Okay, so this statement you're telling the reader, okay, mathematical, this is how your math teacher read it. Okay, X is larger than 2 and smaller than -2. Okay, and the grammar, the syntax of mathematics, that's what it means. Then you say, no, I mean is what I mean is less than -2 or larger than 2. I'm sorry. This grammar, this way of writing mathematically has been determined. It cannot follow your grammar. Okay, it cannot follow your grammar. Okay, so that's why this inequality is a terrible, horrible mistake. Terrible, horrible mistake. You must write it this way. Okay, must. You must write it this way. So this is the first common, terrible, common mistake. Terrible, common mistake. Okay, you need to understand the rule of mathematics. Okay, now in comparison, right? In comparison, when we have absolute value less than 2, remember when we talk about that, remember when we talk about that, right? The solution would be X is between -2 and +2. What does that mean? It means X is larger than -2 and smaller than +2. So grammar-wise, right? These way of writing in chain, they always mean and. They always mean and. Oh, sorry. They always meant and. If you want to mean or, if you intend for or, you have to separate it. You have to separate it, because one grammar of mathematics can only have one meaning. It cannot have different meaning. Okay, now, so this is number 1. Okay, this is number 1. Number 2, which is for this particular question we have at hand, right? In this question, right? For this question we have at hand, which is right here, right? We'll have a situation like this. And some people would make that similar mistake. They will say, oh, -2 larger than 3x minus 5 larger than 2. Duh, look at that, guys. If you treat this number as a single quantity, we do. As a single quantity, can this number be, you're telling the reader that 3x minus 5, okay, this is what you're telling the reader, is larger than 2 and smaller than -2. That's what you're telling the reader. And obviously, that's not going to happen, not in a million years, right? Not even in a trillion years. It will never happen. Okay, so whether you write it this way or some other people may write it this way, okay, they really have invented the thing, they would write it this way. It doesn't matter, okay? It doesn't matter. Some people will write it this way, 3x, right? And they say, and this is going to be larger than 2, smaller than -2. Okay, it means exactly the same thing, which is a mistake. No question about it. So this is one of the most common mistake. Okay, this is one of the most common mistakes. We do have another mistake. This is less common, but it still happens a lot. Okay. The story goes like this. Okay, the story goes like this. So the student, okay, will say, I'm going to use a simple case. Still solve for x. I'm going to use a simple case to explain this, right? Absolute value of x is larger than 2. And these student, okay, and these student, they will write this. They say, oh, then I have to use or, so I am going to use or. So this is going to be less than -2, or the absolute value of x is larger than 2. Okay, this is another mistake I saw. Okay, it's less often than the previous 3 mistakes, but it still show up. It still show up from time to time. Okay, in other words, that this is the sentence, right? This is the if statement, and this student actually augmented that mistake to make it in such a way. Okay, now think about it. Does this one ever have a solution? No, it doesn't. There's no solution, right? So this whole thing is just redundant. You just repeat yourself, but with some unnecessary, confusing statement. Okay, so don't do that. Don't do that. Remove it. Okay, you typically will lose point if you do that. So this is another very common mistake. In our situation, right? In our situation, it could easily be written as, the student could be saying, hey, I'm going to write it this way, right? The student could easily write it this way with similar model, right? And this student will write, hey, this piece is going to be a less than -2, and the same piece is larger than 2. It's the same mistake. It's the same kind of mistake. It's just one is more complicated and one is a little simple. Same mistake. Okay, mistake. If we analyze carefully, right, there's no solution. It should not alter the final solution. But this reflects the student's confusion logically. Okay, so once again, let's look at these, what we did, right? Let's look at what we did, right? These cases. All of these cases, you can see at the end of the solution, we could isolate the variable itself, got rid of the absolute value sign, So here we have absolute value sign, here we don't. Here we have absolute value sign, here we don't, right? So the entire process is to help us to get rid of the absolute value sign and be able to operate algebraically with less constraint, because for absolute value operation, adding, subtracting is very much constrained, right? The adding, subtracting is very much constrained. We talk about what's true and false, right? So we need to get rid of the absolute value. And from these procedures, yes, we can. Okay, yes, we can. And number 5, I like to be reminded. Okay, what is to be reminded? The reason we take so much effort just to get rid of absolute value sign is because the absolute value of any true number, okay, this is false, because this is false. False one's false, right? We have discussed it in the first week. So this is false. So when you do absolute value of addition, absolute value of subtraction, right? This is also false. Okay, another false. Another false is this piece, right? If you have subtraction, false. Now what will be true? Right? Those are false. One is true, one we multiply. Okay, and this is true. So with absolute value operation, we have lots of constraint. You cannot say, oh, absolute value of a sum equals the sum of absolute value. Those are false. Only for a multiplication and division, we can do that. Okay, only for multiplication and division, we can do that. Okay, so this is why that we make all these efforts. We make all these efforts from graph, from analysis, from the function perspective to get rid of the absolute value. Look at that, we get rid of the absolute value. Okay, so let's do a couple more examples, okay? This lesson is fairly long, but very important that you don't make those mistakes. And how many, example number 6. So let's work on example number 7. Okay, example number 7. And this time we still have solve for, right? And solve for x, and the inequality, right? We have 3x minus 1 larger than or equal to 2. Larger than or equal to 2. And the idea is the same, right? Larger than or equal to 2, right? So we have omega, right? This case is a little more complicated situation. And so we have that model in our mind and we understand, right? We understand it. It's very important that we understand it, right? Once you understand it, the rest is just applying it, right? So this is our omega, okay? And we know the absolute value. If the absolute value of omega is at least 2, then omega would be either case or case. This is the or case. You just write that or case, right? And you put your omega in place. you put your omega in place, and then you solve these two inequalities respectively, and make this to be, you know, this is your think out loud, or it's just your, it's something in your head, right? So we add 1 on both sides, so 3x less than or equal to, we add 1 on both sides, we have -1, right? And or we also add 1 on both sides, then we have 3x greater than or equals to 3, right? And then we divide both sides by 3. We have x is less than or equal to -2/3. Okay, I intentionally to choose these numbers. Sometimes you encounter fractions. Okay, I know you guys love fractions, don't you? So you got it. On this side is x is larger than or equals to 1. And that's our solution. You're done. So this, all you have to show is this piece of work. Okay. And I typically would not ask you for interval solutions because I find it's good, but not terribly useful. Not terribly useful. As long as you know how to do it, I'm not going to spend more time there to work on it, right? So you have a negative up to -2/3, and this over here, it's a negative infinity to -2/3 union. Okay, to me, the inequality solutions is more important. Those are my favorite. Okay, I want them to become your favorite too. Okay, if you keep using them, you will find these inequalities are very, very useful for you. Very, very useful for you. Okay, so learn to use inequalities. Why? Because most of the students I have taught in the past in calculus classes, they have demonstrated they are very clumsy with the use of inequalities. Okay, and I wish to improve that condition. So this is example number 7, greater than or equals to 2, right? And what else? The third case, greater than 0, okay? Greater than 0, this is the case, right? So if you have an inequality, right, in that case, right? So we're doing this case by case. Okay, we got them all covered. This is probably example number 8, right? The case we're talking about is right here. And I'm going to make up a story. I'm going to make up a question. Say solve for x once again, right? And we have an absolute value. We want this absolute value to be larger than 0. Right? But of course, we're not going to use x. We've done that, right? I'm going to make it complicated, right? I'm going to have 3x plus 7 is larger than 0. Right? And we understand this model. We know how it works. So the solution would be what? All real numbers, but whatever makes omega equal 0. Right? All real numbers except the number make omega equal to 0. So in other words, anything that make omega is not equal to 0 will be solution. And our omega is 3x plus 7. Okay? And then you get a 3x equals to -7. Oh, sorry, not equals to -7. Okay, so in the end, you get x is not equals to -7/3. That's your solution. And the interpretation, okay, solution, okay, all real numbers except -7/3. That's the interpretation. So this symbol means that. There's another way to express this piece of work. Some people may like it to say, okay, I just need to another way. Okay, this other way to solve this inequality, it could be just say, oh, you know, every number will make it positive except when omega is 0. So I'm going to exclude the number such that omega is 0, right? And then you will go, you need to understand the logic, right? You set it equal to 0, and then you separate, then you get, you know, x equals to -7/3. Okay, you need to know what you're doing. What are we doing? We are trying to identify that number of x such that the absolute value of omega is equal to 0, and we exclude it. We're going to exclude it. So in the end, you also express it the same way. So your solution actually will be expressed the same way. And this is the solution, right? So that is the solution. That is the solution. So there's no difference because equal to -7/3 and not equal to -7/3, they're opposite to each other. If this is a number it cannot be, the opposite can be, right? So you need to understand the logic. You need to understand the logic. So let's look at the other cases. Let's look at the other cases, right? So case by case, we have studied them. We've studied them. And the other one is larger than equal to 0, larger than or equals to -2, right? So I'm going to copy these 3 cases, right? Maybe we can get it done without too much back and forth, right? Without too much back and forth. Here we go. Right, so that case, example number 8, we're done. 7, 8, right, 8 is done. 9, example number 9, right? So that's the case we're going to work on. And we have 2 other cases. We have 2 other cases. Okay, example number 10, right? We have a case there. So we're going to deal with these remaining 3 cases. We're going to deal with the remaining three cases. 11. Okay, so one more case. All right, so let's go. Let's go. Larger than 0, right? So this one is going to be greater than or equal to 0. So I have solved for x, right? The absolute value of, I'm going to say 9x plus 13. And I wish that to be at least 0. Right? I understand my model. I understand the illustration when we did it. Okay, don't you ever get yourself, you know, to be like relying on your memorization. Okay, so I'm doing this provided that you have understood. Now, you know, omega is 9x plus 13. In this case, the solution is all real numbers, right? So 9x plus 3 can be any real number. As a result, x can be any real number. And in this case, actually, you don't need to do anything. Okay, you just understand the picture. Okay, then you just tell the reader the solution is all real numbers. Solution is all real numbers. That's it. Right? Because if 9x plus 3 plus 13 can be anything, then x can be anything. Right? Number 10. Number 10. I can say solve for x. Right? And here I'm going to create a, let's say 5x minus 17. And I want this to be greater than equals to -2. The same scenario, the same scenario. The absolute value of anything, okay? The absolute value of anything, just like in this situation too, the absolute value of anything is going to be greater than equal to 0. And this is anything. Okay? And this is anything, right? You can say the solution is all real numbers from -infinity to +infinity because of what? This absolute value is going to be at least 0, and 0 is larger than or equal to -2. That is always true, right? So that case is covered. That case is covered. And last but not least, we have a larger than -2, didn't we? Did we? Larger than -2. Is that 12? Would that be 12? Okay, we can make it. Okay. So this 12 is addressing that case larger than -2. Okay, we might have covered. I think I'm tired. So let's wrap this up. I might have covered it. I forgot. Okay. So larger than equals to, larger than -2. So it's not a big deal. Let's just do it. Okay, I just want to make sure all the cases are covered. Okay, all the cases are covered. And here we go. Okay, so this is the case that it's larger than -12, right? So I can totally make up another example. Say, hey, solve for x. Solve for x. And here I have an absolute value. Okay, we have an absolute value. And here I'm going to create 5x minus 7 larger than -2. Okay, so what is the solution? We have discussed it, right? The absolute value of anything, right? So this piece is always greater than or equal to 0, no matter what x is. And 0 certainly is larger than -2. Right? So that's the because. So the solution is all real numbers. All real numbers. At this point, I think I'm just going to go back a little bit to explain to you why 0 is greater than or equal to -2. Some of you may be a little bit confused, okay? I'm kind of imagine that might be because when I was in the classroom, this could happen. Yes, 0 can never be equals to -2. But this statement says 0 is larger than or equal to -2. Okay, and you can also do larger than, but equal to -2 is impossible, but larger than -2 is true, right? So true or impossible is true. True or false is true. Remember, true or false is true. So 0 is larger than negative, that's true. 0 equals to -2, that's false. True or false is true. So by truth table. And if you don't feel comfortable, you can just write it down like that. No problem. No problem, okay? But anyway, without further ado, we have covered all of these cases, I think. Okay, if I have forgotten any case, please don't hesitate to bring this up. And I have pointed out all the possible common mistakes I can think of. Okay? So without further ado, I think this lesson probably is super long. And I will see you guys another time. Thank you for watching.